I welcome everybody to the Master's Defense of Jordan Wright. Jordan has been with us for the last couple of years, has been working on a topic that's been funded by a couple of companies, and so we look forward to having him present. This is also part of our consortium for innovation and post-harvest loss and food waste reduction webinar series. So I know we have a few people that are participating remotely. We will open up for questions at the end of his presentation by chat. I will monitor that and ask those questions. We won't open the microphone for that. And then, of course, it'll be open for questions here in the audience as well. And then afterwards, we'll close up, and then the examination by the committee will continue. All right, Jordan, all yours.
Sounds good. All right, thank you for coming. I'll be doing my final oral exam, and my project is titled Advanced Modeling of Stored Grain Ecosystems for Cable-Free Grain Storage Management. This all of a sudden is not working. One second. Oh, okay, there we go. Yeah. All right. So first, I'll talk a little bit about the basic project details and overview to give some context to the work I've done. Then I'll go into the development and then validation of the heat, mass, and momentum transfer model that I developed as part of this work. Next, I'll talk about how I modeled the effects of non-uniformity of airflow through a bulk grain mass. And then finally, I'll talk about a case study I did for a comparison of temperature and EMC-based fan controls, showing the possible utilization of modeling for grain storage management research. So my project is funded primarily by a company called Amber Ag. Amber Ag is a startup trying to replace temperature cables and automate grain storage management. Instead of temperature cables, they have a more simplified system that has a sensor in the headspace and in the plenum. And these sensors monitor the temperature, relative humidity, and carbon dioxide in those two spaces. They also have a fan controller as a part of their system so that they can look at weather patterns and predict the best aeration windows and allow you to have more automation and control over your fan and aeration practices. So the objectives that I had for helping their system out with my work was first to develop and validate a grain storage ecosystem model. Since they don't have cables directly in the grain sensing it, that's where the model comes in to predictively monitor the temperature and relative humidity. I also wanted to begin integrating the model into the Amber Ag system for this predictive grain monitoring and automatic grain aeration management, helping to improve the way they select windows and improve their capabilities by adding modeling to their technology repertoire. And then lastly, I evaluated the effects of non-uniformity of grain mass on the non-uniformity of aeration, cooling, and conditioning. So without temperature cables, they don't have the direct sensing like I said. So that's why we have to have a model that allows us to predict the grain temperature based on recorded weather data and all of the bin parameters. We can run the model with all of that data and then have an estimate of the grain temperature distribution and the grain moisture content distribution. Because the other big function that temperature cables serve is to detect hotspots caused by biological activity that can cause grain deterioration. This biological activity causes an increase in heat, and that's detected by the temperature cables. This biological activity also produces carbon dioxide. And so the Amber Ag system, without directly being able to sense the hotspots in temperature, directly senses the carbon dioxide increase. And then, of course, the model will be used in finding aeration windows and further study of grain management practices. So next, I'll talk about the development of the model. Without going into too much detail on the equations, in the grain mass, we have a heat, mass, and momentum transfer being accounted for. It's important that we account for the heat and moisture transfer so that we know the temperature and moisture content of the grain. And then the momentum transfer is accounting for natural convection. The Concari equations were used here for two main reasons. The temperature equation accounts for latent heat, which is important so that it's coupled with the moisture equation. And likewise, the moisture equation is coupled with the temperature equation with some parameters where the diffusivity is based off of derivatives of the EMC curve. So it takes EMC curve into account when you're accounting for the equilibrium between the air, between the grain, and the grain itself. The boundary conditions are prescribed as systems of ordinary differential equations, essentially energy and mass balances on these boundary conditions, which account for heat loss to the grain, heat absorbed from solar radiation, heat gained or lost due to forced convection from the wind. So all of these things are accounted for in the boundary conditions. And additionally, the way we account for solar radiation allows us to sort of mimic the effects of a north versus south side where you would receive or not receive direct solar radiation. So that, while being a 2D model, allows us to have some investigation into those 3D effects. And then the aeration model was based off of an existing model in Python based on previous FAST models, which have been well documented and well used. It's based on the Thomson equilibrium model. So it's a widely used model that has been used and validated many times before. The numerical methods of this model are very different from the model most recently done by a previous grad student of Dr. Myers, Dr. John Lawrence. His model was very complicated and took a lot of time to run. Some of these simulations took several hours to run, and we wanted to narrow that down to running in a few minutes. And so that's one of the main reasons it's two-dimensional. It uses an explicit method. There's larger mesh sizes. Additionally, it was being done in Python, which is just inherently less efficient than Fortran that the previous model was coded in. But because we have simplified the methods and used more efficient computational methods, it means that it's a much more user-friendly model with a much easier access. So it's more accessible to people and more people can make use of this model because it runs more quickly and doesn't take as much background encoding to utilize. So after the model was developed, the next big step is, of course, to validate the model so that we can trust the results. Model validation for the headspace and plenum was done with recorded data from the Amber Ag sensors. Like I mentioned, the Amber Ag sensors are installed into the headspace and plenum of bins. So these bins were at the ISU research farm, and we were able to compare our model data with these recorded data points from Amber Ag. The aeration model was validated through comparison to the Lawrence dissertation, and the non-aeration model was also validated through comparison to the Lawrence dissertation. This is the graph for the headspace model. As you can see, we have pretty good agreement following the daily trends of heating and cooling throughout the day. There are a few spots, especially in the early portion, where we're over predicting the temperature right at the peak temperature due to over prediction of the effects of solar radiation and maybe under prediction of the effects of forced convection, which would bring that down. But every nighttime temperature is very, very accurate when there's less solar radiation. So when you average everything out, the standard error ends up at 6.4 degrees, but the rolling average error is only 0.72. And so these daytime highs really are exaggerating why this standard error is so high. But the rolling error, the average error over the whole period is pretty good. And that's what's most important for the diffusion of heat into the grain mass. Daily temperature spikes are not going to have a huge impact on the overall accuracy as that diffuses in, which is why I've also included the average error. The same is true for the plenum model, where we have some under predictions at the start of the run, causing a standard error of 6.7, but an average error of negative 1.9 degrees. Next, we look at the aeration model. So here we have our model overlaid over the results from the Lawrence dissertation here. So our model is this orange line, the current model. The blue line is the Lawrence model, and then the red line is the recorded data from the work in the Lawrence dissertation. So this looks at the center cable for a bin, and we have the bottom node, the middle node, and the top node of that cable. So at the bottom node, we have around 0 to 2 degrees Celsius error throughout the entire run. The main sources, the main areas where it deviates is in the afternoon of the 11th and the 13th. I thought it was interesting. You see that's also where the Lawrence data overpredicts by more so there, but being at the same time, I thought that that could point towards a difference in the recorded weather data and the actual local data that's experienced, because we can only be as accurate as our weather file, which is usually recorded from a weather station nearby. But overall, the aeration front is well tracked, and we capture the movement of cooling and then rewarming, and this pattern is generally pretty well captured. In the middle node, it's about the same story. It's pretty well captured, around 0 to 2 degrees error. We have the main over-prediction of temperature here at the front, and then very good, we're no longer over-predicting in the afternoons of the 11th and 13th. We no longer have those premature temperature spikes. Lastly, in the top node, we see that error over-predicting in the front has increased. It looks to, you can see that it's the angle is less steep and the movement is just delayed. It's lagging behind or a little over dampened. This could point to differences in the actual airflow rate and the calculated airflow rate based on the bin dimensions and fan specs. So one thing that's important here is that we see this wave, this like dampening effect. When we look at the bottom node to the middle node to the top node, you can see the waves sort of stretch out and delaying those effects. So that's something that we see in aeration in both the recorded data and in our model. So looking at aeration, the center cable shows pretty good agreement model to recorded data. We can see the wave dampening shape and behavior of the model throughout this cable and what we've looked at. And we know that airflow is definitely a key parameter in modeling aeration. Next, we look at the non-aeration model. So in addition to all of the lines that I mentioned, we still have our model is the orange line, the Lawrence model is the blue line, and the recorded data from the Lawrence work is the red line. We additionally have the light blue here is the ambient temperature, just added to sort of show the ambient temperature and add some context to the cooling and then rewarming of the grain mass here. So here in the bottom node, we have a 2 to 4 degrees Celsius prediction pretty much throughout the entirety of the run. Obviously, we start at the correct conditions because that's the input, and then it's generally under predicting by about 2 to 4 degrees throughout the duration of the run here. In the middle node, we see the same trend where we begin to under predict here, but it does begin to course correct a little bit through April and May. It gets a little bit closer here. And then finally, in the top node in this simulation, we again start off with an under prediction through February and March, and then it corrects by May. It is generally in line with the recorded data here. So overall, for the non-aeration, the cable shows pretty good accuracy, and we're capturing those cooling and warming trends that would be expected over a storage period during these kinds of conditions. The next thing I looked at was the effects of non-uniform airflow through bulk grain mass. So in addition to working with Amber Ag, I also worked with another company called Grainweevil, and they developed this robot, the Grainweevil robot. And so the Grainweevil robot allows you to not have to enter dangerous grain bins. It can break up crusting or level grain without someone having an actual human enter the grain bin. So that saves on just increasing the safety factor. But what my work was focused on was really proving the potential effects of the Grainweevil. So in having even airflow, there's two main problems that we tackle. when grain is just poured into the grain bin, we have a peaked grain mass based on the angle of repose, and then there can be a concentration of fine matter, which decreases the porosity and increases the resistance to airflow. And both of these things slow down your aeration progress in the center of the bin, which is inefficient and leads to excess run hours. What the grain weevil robot claims to do is you could add it after filling a bin to spread out the grain mass. This wouldn't affect the concentration of fines, but it would remove the peak without a person having to enter the bin. And then it could also be added with the grain mass to spread out every load that you add to a grain bin. And if it can keep up with the rate that the load is being added, then you could spread out the fines and also end with a level surface. The grain weevil at this stage isn't capable of doing that, but we were able to use some modeling efforts to show sort of a proof of concept to really show that it's possible if the grain weevil robot can get to a place where it can spread out these fines, just to show the effects that that could have on uniformity and efficiency of aeration. So to model this, we used ANSYS Fluent, a commercial CFD software. So we had our different scenarios where we had just regular peaked grain, leveled grain, which is the grain weevil being added after filling, just leveling it without changing the distribution of fine matter. A partial spreading scenario, which would assume that the grain weevil has been added before filling and has spread out every load as it's been entered. So it is a leveled surface and also a partially spread out concentration of fine matter. So it's less concentrated in the center and more evenly spread. And then just some ideal grain spreader that we're just going to assume perfectly spreads out everything evenly, mostly as a sanity check. And so this geometry and porosity values were entered into the ANSYS Fluent model. We ran the Fluent model. That gives us a velocity profile, the velocity at each portion of the grain mass. We were able to analyze the velocity profile, turn that into a non-uniformity factor, which I'll discuss in more detail in a few slides. That non-uniformity factor becomes a parameter in our aeration model to vary the airflow rate from the center to the side. And having that parameter added to our aeration model means we can show aeration results and really get some quantifiable real-world or simulated examples to show the effectiveness and potential benefits of the grain weevil. So the first thing, in addition to the velocity profile, we also generated static pressure to show the fluid flow movement. Fluid flows from an area of high pressure to an area of low pressure. And so these predominantly horizontal static pressure lines means that there's predominantly vertical fluid flow, mostly one-dimensional outside of a couple areas where there's some slight non-one-dimensionality, but in general, it's very one-dimensional airflow, which is an important assumption for our aeration model. Looking first at the peaked grain results, the first thing that we notice is these extreme values, extremely low values towards the peak and extremely high values towards the edge of the grain mass. So when we're looking at this here, the center of the bin is on this side, the wall of the bin is here, and then this is the plenum and the surface of the grain mass here. When we take all of these velocity values and plot them here being the center right there, and then going out to the radius, the blue nodes here is every value of velocity. So you can see these extremely low values, that's this here, the extremely high values, those are shown here. And then the orange is the vertical average, so the average in that vertical grain column. And we notice that the average still becomes fairly linear. So that makes it a lot easier to account for in our model with a single value of the non-uniformity factor. Outside of that top layer, we see that there's a pretty even radial distribution here where it's fairly consistent vertically in the middle, and it starts off at a pretty uniform velocity. Moving on to the leveled grain mass, we still see it the velocity initially starting at a fairly uniform velocity and then moving to a radial distribution. But in this case, we don't have a peak, and so there's no extreme values that are substantially higher or lower than the average in that top layer. The same is true in the partially spread case, where we have an initially uniform velocity, which moves to a mostly radial distribution but this one is even less spread, even less of a gradient of velocities than the leveled grain mass. So with these, these were all shown for a 36-foot by 36-foot bin with 1 CFM per bushel. We also simulated a 90-foot bin with a 1/10 of a CFM per bushel, and we had the exact same trends between the peaked, leveled, and partially spread grain masses. So big takeaways from the CFD simulations. The static pressure shows predominantly one-dimensional fluid flow. The main extreme values are isolated in the peak of the grain mass in that top layer, and that other than that, velocity starts out uniform and then moves to a radial distribution, which is what predominantly predicts the average velocity throughout that grain column. And so this average velocity is what was used for our non-uniformity factor, which is essentially the difference between the center and the side as a percentage of the average airflow rate. So these are all in percentages. So we can see that the 90-foot bins had slightly higher non-uniformity factors, and that also leveling the peaked grain mass would result in a decrease in non-uniformity, and that also partially spreading the fines in a leveled grain mass or a peaked grain mass would also decrease the non-uniformity. So both of those cases of the grain weevil's potential use have lower non-uniformity than the peaked default case. Next, we plugged those non-uniformity values into the aeration model so that we could get some context to really how this affects everything. So here we have the peaked, the leveled, and the partially spread scenarios. So when we look at these, we notice that the non-uniformity has a big impact on how far apart these lines are at any given point in the simulation. Here in the leveled grain mass, there's obviously a huge distribution, especially right here. If we waited till our side cooled, the center is nowhere near being done with its aeration progress. And by the time the center has cooled, the aeration front has long since moved past the side, and because we've just assumed constant aeration here, it's actually rewarmed since then. So if, say, the target was to cool from 20 degrees Celsius to 10 degrees Celsius, in this case, we never really reach a point where both of them are at that value. In the case of the leveled grain mass, we do reach that value right around 175 hours in. Both the center and side are below 10 degrees Celsius. And then in the partially spread, the most uniform, we see that at around 150 hours, both the center and the side are below 10 degrees Celsius. So there's potential for savings in the fan run hours here, which can save environmentally and just save costs on energy costs. And so this is because there's more efficient aeration in these more uniform grain masses. Because you're waiting for this slower center to move in the peaked grain mass, it's overall less efficient because you've already completed your objective in the side and you're just waiting on the center to complete. So when they're more uniform, it's more efficient because the center and side move much closer together. I also did a simulation for drying in this case. We see much the same results here when we're drying. So here we see the peaked, the leveled, and the partially spread cases. And this is looking at the average moisture content of the center grain column and the average moisture content of the side grain column. So we see that the non-uniformity factor has a huge impact on how close these lines are and how similar it is when you have if you were monitoring your center or your side, how far apart they are. Additionally, like the cooling case, there's potential for fan run hour savings. If, for example, 15.5 was your target, we have that being reached at around 1,300 hours because it doesn't matter when your side gets completed. We have to wait till the center has dried. So that happens at around 1,300 hours, but by then we've shrunk our side by quite a bit. Oops, wrong way. In the leveled grain mass, we achieve our drying goal in the center at around 1100 hours, and we've shrunk by a little bit less. And then in the partially spread case, we've achieved our goal at around 1000 hours and shrunk by even less. So again, having more uniform grain mass allows us to achieve all of these objectives more efficiently because we're not waiting on that slower moving center. So in conclusion, when we're looking at this, we know that the leveling of the peaked grain mass or the partial spreading of fines and leveling of a peaked grain mass both decreases the non-uniformity in large and small bins. Decreasing this non-uniformity can save run hours and increase the efficiency for cooling and drying. And because of that, that means that the grain weevil robot does have the potential to save farmers money by improving the uniformity of aeration during cooling and drying. And so these results we gave to grain weevil so that they could apply for phase 2 funding, and had a pretty good proof of concept showing the potential there. Next, I looked at comparing temperature-based and EMC-based fan controls. This chapter really looked at how can we utilize the model to improve grain storage management. So here we're looking at a very simple case. We want to cool our grain down before we store it to prevent grain deterioration. However, we know that if we're cooling grain only accounting for turn on the fan when the temperature is cold, then we're at risk of overwetting or shrinking the bottom layer if we're not accounting for the equilibrium moisture content and the humidity of the air that we have when we select our aeration windows. And so modeling allows us to very quickly look at a couple different examples of fan controllers and also predictively monitor based on forecasts what might happen based on different fan controls. So here we're assuming we have a 1 CFM per bushel bin. The bin starts at 20 degrees Celsius and 15% moisture content. And we are assuming the fan controller at midnight every day looks at the next 24 hours, uses some logic controls to select valid aeration windows. For the next 24 hours, it runs those windows. And then at the end of those 24 hours, it checks, have I accomplished my goal? In this case, the cooling goal is to cool to an average grain temperature below 5 degrees Celsius. So for the temperature-based controls, we're only looking at temperature. We're just going to say turn the fan on whenever the ambient temperature is at or below 5 degrees. For the EMC-based controls, we also want the temperature to be at or below 5 degrees Celsius, but we also add the stipulation that we want the EMC based on the ambient temperature and relative humidity to also be below 20%. So looking at the temperature-based controls, after day 1, 11 hours get selected. Our average temperature has lowered to 9.4 degrees Celsius. However, the bottom layer, the bottom 1 meter of the bin is now at an average moisture content of 15.5. So it's overwetted by 0.5%. By day 2, 27 total hours have been selected for the temperature-based controls. We've almost achieved our target. The average temperature is now 5.7 degrees Celsius, but the bottom layer has increased to 16.5% moisture content for the average of that 1 meter bottom layer of this bin. And finally, on day 3, the simulation has completed after a total of 38 fan run hours over that 3-day period. It cools the bin to 4.3 degrees Celsius, so we've achieved our cooling objective. However, without looking at the EMC for our fan run windows, we've selected some fairly humid air and end up with a bottom 1 meter that has an average moisture content of 16.9 and goes up to 17.2. So this being well above the safe storage moisture content for corn would have some big concerns if we were cooling for storage. If we leave the corn for storage at this moisture content, we're definitely putting ourselves at risk of molds or other biological activity. Next, we look at the EMC-based controller. So here by day 3, we've only selected 4 hours because it's much more selective on which windows it will approve for aeration. So in those 4 hours, we haven't achieved much cooling. We've only gotten down to an average of 14.8, and the top of the grain mass still just remains at 20 degrees. However, our bottom layer has not overwetted. It's actually shrunk just a little bit to 14.8%, which is expected when we're cooling grain to shrink slightly. By day 8, 10 total hours have been selected by the EMC-based controller. We've lowered our temperature to 9 degrees Celsius, and the bottom one layer is actually right at the starting point of 15% moisture content. By day 11, 18 hours have been selected. The average temperature is at 5.7 degrees Celsius, and the bottom layer 1 meter has overwetted just slightly, but to 15.1% moisture content. And finally, after a total of 12 days and a total of 13 hours of aeration, our average temperature is down to 3 degrees Celsius, and our bottom 1 meter layer is now at a moisture content of 14.9%. So when we compare the two final outcomes, the temperature completed in 3 days and 38 hours, while the EMC-based controller completed in 12 days and 34 hours. They both achieved the cooling objective, though the EMC-based controller does achieve a slightly more cooling with slightly less hours. Where the real difference presents itself is in the moisture content. It's at the bottom layer. The bottom layer moisture content in the temperature-based controller is at 16.9%, while the bottom layer of the EMC-based controller is at 14.9%. So that's a 2% difference and would be cause for concern in the temperature-based bin based on its moisture content, but would not be a cause for concern in the EMC-based bin. So the conclusions are that the EMC-based fan control can achieve the same or better cooling without substantial impact on the moisture content. And also we found that EMC controllers are more selective, which will result in more days being required to find these suitable fan run hours. So that concludes the chapters that I've done, but of course we have lots of ideas for how this model will continue to be used and help us in research and with Amber Ag. So first, I made this model for Amber Ag through their funding. So of course, Amber Ag is going to continue to utilize the model. They'll utilize it to replace temperature cables so that users can have an understanding of what the temperature and moisture content is in their bins, and also have an understanding of how much aeration, drying, warming, reconditioning progress they've made based on their aeration. They'll also utilize the model to continue investigating how they select their aeration windows best, and using the model to add features for their users, basically. Of course, ISU will continue to utilize this model, especially at the ISU Kent Corporation Feed Mill and Grain Science Complex. All of these bins will be equipped with both the Amber Ag system and the AGI SureTrack system. So they'll have sensors in the headspace, the plenum. They'll have cables in the grain mass that are temperature and moisture cables, and we'll be able to continue generating a lot of data for different larger bin sizes, different grain types, whether the fan is, how well the fan is sealed. All of these things will be able to have a lot more comparison and validation of the model. And then, of course, we'll continue to use the model for studying grain storage management and grain storage management strategies. Lastly, the model I see as a very good teaching tool because it uses like totally different numerical methods than some of the previous models. That makes it a lot more user-friendly. Really, all we have to change for a user is these five files, and they're just text files that you can edit in any text editor. You can put them into the right folder, hit run, and then the model will give you your results. So it's very easy to use the model even without a strong background in modeling or coding. Additionally, because it runs very quickly, it's something that Amber Ag will eventually house on their servers and have a browser-based tool that likely runs a simplified version of the model. Maybe you can add in your location, bin diameter, or bin dimensions, grain type, and then run some simplified version of the model. So I think that that's because it runs so quickly. Aeration simulations like the ones shown in the fan controller study, those run in 5 to 10 seconds. So something that could be used in a classroom or during a professional development like the grain quality management, we could show the effects of this very rapidly and very hands-on. Someone can adjust the parameters that they want to use, hit run, and have results in a matter of seconds. So I see this as a very good teaching tool as well. I'd like to acknowledge mostly Amber Ag was the primary sponsor of this research through National Science Small Business Independent Research Phase 2 funding, and then the non-uniformity chapter also funded by Grain Weevil through their National Science Small Business Phase 1 funding. So that funding was critical to me being able to do a master's and very important to this research. So now that concludes my presentation, and I'm ready to field any questions. Yeah, you can.
Any questions coming?
Good question. So the question was, what were the considerations for the errors and for the allowable ranges of those errors? So first, looking at the headspace and the plenum model, these errors that we chose, the main concern for these is that is the error of the boundary conditions going to limit the error and possible accuracy of the actual grain mass? Because the values of the grain mass is what's most important. And so what we found was that because the average error is pretty accurate, if you really take the rolling average over the kind of time span that it takes for the headspace temperature to really diffuse into the grain mass, when you take the average of those, it's pretty accurate. And so those spikes in the day-to-day spikes didn't end up having a huge impact on the overall accuracy of the model. Additionally, since Amber Ag has sensors in the headspace and in the plenum, they're constantly generating data that we can continue to improve. Of course, we'll continue to improve these models, adjust the way we account for convection and solar radiation. And additionally, because we have measured values for these kinds of boundary conditions, we don't even need the model for, if we are just running recorded weather data to get our current conditions, we can actually just superimpose the recorded Amber Ag data for those values. And then for the actual grain mass, we had pretty similar error to the Lawrence model. So we thought that was a pretty good sign, somewhere in the 2 to 4 degrees or for the non-aeration and 1 to 2 for most of the aeration model. This gives you a good understanding of what your grain temperature is, how much grain progress you've gotten, and without the no longer having the costs of the temperature cables, we thought that's a pretty good compromise between having nothing in your bin to determine your temperature or spending the money to get a full set of grain cables, having just 2 sensors, a much less expensive system, and this model that's within 2 to 4 degrees we thought was a pretty good compromise. So I think that it's definitely utilizable, and Amber Ag has already started integrating the model into their system. It's not fully functional for customers, but we've already started comparing our model to customer data and having pretty good results with tracking what they've seen.
Also, do you see that this kind of way to solve these kind of
Yeah, so the question is, how could this model be applied to smaller things like PICS bags and hermetic storage? There has been modeling work on hermetic storage. One of Dr. Rosentrader's grad students actually did a modeling paper on this kind of modeling in hermetic storage bins. So it is being done, and it has been done. One thing that's beneficial actually is smaller bins like that. The effects of natural convection are generally much less. So in a hermetic bin that's very, very well sealed and is much smaller, it'd actually be much easier to develop this kind of model. The real question would be just modeling the conditions that it's around would become different. It'd basically be like the wall model just all around. So it would actually simplify things a lot having smaller cases. Good question.
So if you, so, you know, how would, in terms of where you are and you build it for some set up model station with perhaps building right down to where station was, get good data collected and viable with it, but had the previous data from the local, how would you set up a
Good question. So the question is, how are we going to proceed further validating the model with the bins at the ISU Kent Corporation feed mill and grain science complex? So these bins having so many sensors and being more in our control, I think it'll be important to have a longer period of non-aeration. So when we have the control for a fully controlled trial, we want to put the grain mass in there, level it, and then just leave it for a very long storage period so that we can get storage over when it's right after harvest, and then being able to see it like cool and then warm for like a full duration of the storage period so that we can model different climates. Like in the bins that we mentioned, we only really had like a month between when it was different aeration times and when it was being filled and loads were being taken out and it was being cored. The period that we had to simulate was actually pretty small. Additionally, we will have more control over its brand new cables, brand new sensors. We can seal the fans really well and know how well different general precautions are being taken. And just having more data points, having 4 bins means we can have, even if only one is dedicated to the validation, just being able to generate more data sets so that you're not relying solely on one data set for your validation will also help. And then having different grain types that we can validate, whether or not your fan is sealed, that's something that we know will probably impact, especially the effects of natural convection. The size of the bin will definitely have an impact on your natural convection. Being able to really just have that flexibility in validation is going to be critical to implementing the model further.
how long do you let grain set there? Question is, how fast do we use? Let it set for 6 months? They're using grain today.
Yeah, I guess we'll have to ask Tony on that if he can spare one. But that's my ideal case for validation.
Do you know what our overall use is?
I don't off the top of my head.
So the field and run. Grain elevators. But we have a study. Yeah, but the form that we put. No, doesn't have. Yeah, to think of this. Service business. Or if there's grain going into that has to be some form. Purpose off. So we could designate 2 5 and 8. But it can run independent. 5,000. So one run independent study. better make some money on storage. Now we gotta come up with creative ways to do it. Yeah. No, that's a good question. Yeah, but the whole idea is that we can't run two facilities independent of each other because of that. Question coming in on the chat. Excellent presentation regarding its practical application. How will the size of the silo affect the prediction?
Good question. So the question is, how does the size of the bin affect the predictions? There's a couple of things that come into play with the predictions here. So larger bins, we know, have larger natural convection currents, and also, so the model here, like what we've seen in our validation, the Lawrence dissertation was on pretty small bins. These bins are 2.7 meters in diameter, so they're fairly small. Larger bins, we would expect to have a larger impact of natural convection. Larger bins also, you might have differences in your headspace and plenum temperature between the center and the side. There have been models that have modeled these differently, but we modeled this as just one value, mostly because working with Amber Ag, it makes most sense with their hardware to just have one value for the headspace and one value for the plenum. But in a very, very large bin, it's possible that the headspace air in the side might be warmer than the headspace air in the middle, just because it's closer to that roof and there's less mixing. And then additionally, bigger bins or bins that have another big critical factor is how well sealed your bin is. That's going to have impact on how much ambient winds impact the convection currents inside, and especially how well sealed your fan is going to have a huge impact on the actual temperatures of your plenum and headspace. So those are all like key parameters that need to, more research needs to be done to really get exactly how we fine tune the model for specifics of these bins. But that's the idea for having more bins to test and more data to gather. So good question.
Good. All right. Thank you. Unless there's any other questions, thank you. Close out the webinar. You can say a couple of comments on the webinar coming. When? Next week?
Monday?
Next week, Monday?
Next week, Monday?
And appreciate people joining us, and we'll take a break and before we.
Okay. Thank you, everyone, for attending. Have a great day.